over 2 times this length. So in this case, this length must be square root of 3 in magnitude. So if you look at here, square root of 3 times the RMS value of the per phase voltage, right? And the angle is equals to phase A angle plus 30 degrees. Because if you shift from here to here, and this angle is 30 degrees. This angle is 30 degrees, right? This angle is 30 degrees. So in this case, what we find is for Y connection, the line-to-line voltage, what's the magnitude? Magnitude is square root of 3 times the phase voltage, right? Phase voltage. What's the angle of line-to-line voltage? It is 30 degrees leading ahead of the phase voltage in phase, right? Good so far? Any questions, anything?
You said the line-to-line voltage was 30 degrees ahead of the...
Here, 30 degrees ahead of the phase voltage. Okay, line-to-line voltage is 30 degrees ahead of phase voltage. Because if you shift this vector to here, if you shift means this line is parallel with this line, right? So this angle must be equal to this angle. So this angle must be 30 degrees. This angle must be 30 degrees. So the phase voltage and line-to-line voltage relations for Y connection, everybody need to remember what. So every time, if in your exams I say, I have a 3-phase synchronous generator, the terminal voltage is some kind of voltage. So in this case, every time we say terminal voltage, we're referring to what voltage? Line-to-line or line-to-neutral? Referring line-to-line voltage. Line-to-line is something we can actually measure. So every time we see line-to-line voltage, another way to call it is the terminal voltage. Terminal voltage. Right? Terminal voltage. So that's the first thing we need to remember. And for Y connection, the terminal voltage, the RMS magnitude is equal to square root of 3 times the per phase voltage magnitude. And the angle is how many degrees leading? 30 degrees leading. Always remember that, right? The angle is not that important, but the magnitude is square root of 3 times that. So you have to remember this, right? And everybody have did the lab. So how's the lab called? I mean, did you verify the square root of 3 relations? Yeah. Okay. So this is straightforward. Okay. And next example is delta connection. For delta connection, basically, this is what happens. So basically, everything is hooked up from head to tail, and head to tail, right? So this is head to tail, head to tail, head to tail. So basically, those 3 devices are hooked up in triangular shape. For this system, I need to erase this piece of paper. I haven't finished the Y connection yet. I know I missed something. Okay, so for Y connection, basically, what I see here is, first, we know that for Y connection, I know I missed something here. For Y connection, line-to-line voltage is equal to square root of 3 times phase voltage. And the angle is how many degrees leading? Angle is
30 degrees.
30 degrees leading, positive 30 degrees leading. All right? So that's the representation for it. And also, the line current is equals to the current per phase. The line current is equal to the current per phase. So I forgot to talk about the current. And the current in each line is equal to the current per phase. Well, I haven't given any definition yet, right? So basically, how do we define line to line? By the way, how do we define line to line? Line to line is basically the between each terminal, between the transmission line and transmission line, between the transmission line and transmission line, right? So that's line to line. How about the phase? The phase is the voltage across each element, each device is called the voltage per phase. It's called the voltage per phase. And how about the phase per phase current? It's the current passing through each device, right? So in this case, the line current is equal to the phase current for Y connection. This is the Y connection. And next one is we talk about delta connection. Delta connection is a little bit different. So here's a delta connection. So in this case, for delta connection, this is the case. The device is hooking up with other device. So this is a head to tail, head to tail, head to tail. So in this case, the voltage between each line, is equals to the voltage between, well, across each device. So in this case, the first thing what we find here is, first we look at line-to-line voltage. Line-to-line voltage basically is measuring the voltage between the transmission lines, right? Between the transmission lines. However, if you measure this voltage, basically it's equal to this voltage, and this voltage is the voltage across each device. And the voltage across each device is called what voltage? It's called a phase voltage. So the thing we find first is line-to-line voltage is equal to the voltage per phase. It's equal to the voltage per phase. That's the first property we find. And the second property we find is if you look at the current, and the current that is incoming from each line, this is IA, this is IB, this is IC. It's no longer equal to the current that flow across each device, right? So in this case, the line current is no longer equal to the phase current. And in this case, if you look at the phasor diagram, so in this case, what we have here is we have phase current, IAB, IAC, and ICA. IAB, IBC, and ICA. And in this case, according to KCL, at each node, IA is equals to what? It's equal to IAB minus ICA, right? According to KCL, this is what we find. So in this case, if you do vector subtraction, what happened is I can solve IA. IA is basically equal to IAB minus ICA. So this vector is equal to this vector. You shift it, right? You shift it from here to here, right? So in this case, if you look at here, what happened is there's a still square root of relations. However, this vector is 30 degrees lagging behind. This is 30 degrees. This is 30 degrees lagging behind of the current phase. So in this case, the line current is equal to square root of 3 times the phase current. And the angle is 30 degrees lagging. It's 30 degrees lagging. Right? It's 30 degrees lagging. So let me draw this again. So this is point A, and this is point, where is that? Point B, point C. Point C. So in this case, this is IAB, this is IBC, this is ICA. Right? This is ICA. So in this case, if you consider at node A first. So for node A, IA is equals to IAB minus ICA. So if you consider the phasor diagram, this is IAB, IBC, ICA. So basically, you are doing the vector subtraction. So this is your IA. So the magnitude is still 30 square root of 3 times the phase magnitude. However, the angle, if you shift it here, this is 30 degrees, and this must be 30 degrees. So it's 30 degrees lagging behind. It's 30 degrees lagging behind, right? Go so far, and then yes, questions?
Your IC, IB terms, are those supposed to be swapped? Because on there you have point C, but then you have IB. Not that it's a huge deal, but on the board. What you guys.
Yeah, that's right.
I didn't see it up there.
So in this case, if you look at IB is equal to IAB IB is equal to IBC minus IAB, right?
Yeah.
So IB is right.
Yeah.
IB is right. Let's look at IC. IC is equal to ICA minus IBC, right? So this is also right.
He's just saying, node C there, you have IB going in there.
I didn't, you just wrote it backwards. See where you have your point B, you have IC and
Your line demonstrating.
Oh, my input
On,
card.
on the board, if you go bottom left corner, you see you have IB going in.
Oh, okay. So, yeah, this is actually.